Hello, in this lecture we are going to start with electrostatics. And as you're aware that electrostatics deals with the study of charges at rest. Okay, and at the very start we are going to deal with electric field and the concept of electric field. And since your classes, like elementary classes, you know uh, you know that how the force between the two charges is governed by Coulomb's law. And as you as we look all along, we're going to see some other description of the same concept. That description is referred to as the concept of field. Okay, so just we'll start as people will join. So I'm waiting for a few minutes for people to join. Then we shall start. So today we are going to start with electrostatics. Okay, and we'll start with very basics, and then we'll go along. Okay, uh, just give me a minute. Just give me a minute. Okay. Okay, so let us start with electrostatics. Okay, so as you know that electrostatics is a okay. So electrostatics is a study of charges in at rest. Okay, so electrostatics we are going to deal with charges at rest. So as long as charges are at rest, we are going to deal with something called as electrostatics. Okay, first thing is this. Okay. So whenever charges are in dynamism, or if you see that charges are moving, then we are going to study something called as current. Okay. The first thing is very much clear that a static charge always produces an electric field around it. And what is electric field that we come to understand? Don't worry about it. It is going to propagate something called as electric field. A moving charge, or I would say a charge with uniform motion. Okay, so charge with uniform motion. If there is a charge with moving with uniform motion, then it will produce a magnetic field. And if the charge is an acceleration, so an accelerated charge produces electromagnetic wave around it. Okay, so these are some of the basic points that you should remember. Okay, now one of the most fundamental laws that you already know is called as the Coulomb's law. One of the most fundamental law that you already know is called as the Coulomb's law, which dictates the force between the 2 point static charges by this particular expression. That is, if there is a force Q1, if there is a charge Q1, and if there is a charge Q2, and both of them are separated by a distance of r, then the force between the force between them is in magnitude is given by kq1 q2 upon r square. This is quite clear. And if it and it always acts in the radial direction. So this basically it is a kind of a central force only. It is a kind of central force. And what is a central force? A force which acts between the line joining the two two things. For example, it may be masses, it may be charges. So basically, if it acts along the line joining the two uh, of the things in question, right? Right now, these are the charges. If they are masses, and somebody asks what is a gravitational force is also a central force because it always acts along the line joining the two point charges, point masses, whichever whatever is the context. Okay, so for example, if I'm talking in sense of electrostatics or electric field or things like those, I would say that the force acting between the two charges acts along the line joining the two charges. Is that clear? So these such forces are called as the central force. Okay. Now let's say if these one thing that you should remember since you're starting the subject, one thing is very much clear. One thing you should keep clear that never try to use the sign of the charges. Never try to use the sign of the charges. This is advice that I'm giving to you. Never use the sign of the charges. Rather, just see just see what kind of force it will be. Like for example, if these are opposite charges, uh, like Q1, Q2 are of charges of contrary nature. That is, if Q1 is positive and Q2 is negative, or if Q1 is negative and Q2 is positive, then obviously the force will act in this direction. So for example, if Q1 and Q2 are of contrary signs, for example, Q1 is positive, this is Q2 is negative, so it will try to attract. And similarly, Q1 will also attract Q2 if these are of contrary charges. If Q1 and Q2 are of contrary signs, and if they are of the similar signs, if Q1 and Q2 are of the similar signs, then they will try to repel each other. Okay, and and okay, okay. So is that clear? I think this is quite clear.
Yes, sir.
Okay, good. And let's say let's say I would use some sort of subscript in order to make you all the more. Let's say R12 vector. Let's say R12 vector, which is vector which originates uh, at 2 and terminates at 1. Let's say this is R12, terminates at 1. So basically what R12 means, it originates at 2 and it terminates at 1. Okay, this is what I'm writing R12. So let's say if these two are the charges, Q1 and Q2, and for example, let us take that, what would be R12? So I'll just make a line here. R12 means the vector that originates at 2 and terminates at 1. So this will be R12 vector. And if I mark this direction, this will be R21 vector. Is that clear? I've just given the notation. So I will be following this notation right now. Okay. Now
Yes.
let's say I'm trying to find the force on charge Q2. What will be the force on charge Q2? It will be, and let's say Q1 and Q2 are of same sign. Now let us think about this. Let's say Q1 and Q2 are of the same sign. Then force on charge Q2 would be in this direction, right? So this will be K Q1 Q2 upon R12 per square, or I should write it because this direction is this, so I'll write R21 per square times R21 cap. Is that clear? And if you're aware that the unit vector is given by vector divided by the modulus, so this will give you the answer as K Q1 Q2 R21 vector divided by R21 ka whole cube. Is that clear? This will be, sorry, force on 2 due to 1. Is that clear? Harshit, is that clear? I think it's clear.
Yes,
So
yes.
move ahead. So this is the vectorial representation of the force. So this is how you
Yes.
represent your uh, force in the vectorial form. This is the vectorial way of representing the force vector. Is that clear? Another one of the most experimental behavior with regards to, you can say, with regards to the forces between the charges, and this particular experimental fact is called as the principle of superposition. This particular principle is you should remember that this particular principle is one of the experimental facts. Okay, principle of superposition. And what does it mean? Let's say you have this charge Q1 here. Let's say this charge Q2 is here. Let's say you have this charge Q3 is here. Let's say Q4 is here, and there are n charges. That there are n charges. Okay. Now, what happens is that the force on Q2 because of Q1 remains the same. It is not going to get disturbed because of the presence of the other charges. Okay. So what happens is that if you want to calculate the total force on, let's say, charge Q1, so this will be due to charge Q4 independently. This will be force due to charge Q2. This will be force due to charge Q3. This will be force due to charge Q4, Q5, Q6, Q7, Q8, dash 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 Qn. So force acting upon the charge Q1 is independent of the presence of other charges. So basically, what does it mean? So total force on charge Q1 would be nothing, but it will be equals to what? It will be equals to K Q1 Q2 upon, let's say, R12 per square, and then K Q1 Q2, and I would write R12 cap K1 Q1 Q2 upon R13 square, and then there will be R13 cap, and so on and so forth, divided by R1n per square and R1n. Is that clear? So this
Yes,
is
sir.
sometimes this is something called as principle of superposition of the charges. This is called as the principle of superposition of the charges. the principle of superposition of you can say of the vector force vector here. Of, okay, this is called as a principle of superposition. Okay, and understand that this particular fact is an experimental fact. Okay, so this derives its this is an experimental fact. Okay, now what happens is till now, and I think you are aware that what is K? I think K is you're aware.
Yes,
I think you should aware that K is nothing but it is equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of the free space. This is
yes,
permittivity of the free space. Okay, and the value is I think 8.85 into 10 raised to power minus 12 farad per meter. You later learn that the farad is the unit of capacitance. If you are not well acquainted with this, then this is 10 to the power minus 10. Then I can write coulomb square divided by Newton per into meter. Okay, so this is how you write it. So basically, what is there? If I have to find the charge on Q1, then I have to calculate all the forces due to all the charges which are present. So basically, what happens is if I want to find the force on charge Q1 due to Q2, it will remain undisturbed or unperturbed due to the presence of other charges. So basically, what will happen? What will be force due to charge Q3? What will be force due to charge Q5? What will be the force due to charge Qn? What will be the force due to charge uh, Q4? And so on and so forth. And all you need to do is you have to add all these forces vectorially, and this will give you the net force acting on charge Q1, and this is referred to as the principle of superposition of any sort of vector. Here the vector is force vector. Okay, and K here signifies 1 upon 4 pi epsilon naught, where epsilon naught is the permittivity of the free space. And if you want to write it in this fashion also, I'll write it here also. And what is in general K? I think 1 upon 4 pi epsilon naught in SI unit is I think 9 into 10 to the power 9. Is that clear? Is that fine, Harshit?
yes, yes.
Uh, is that clear?
Yes, yes.
Okay, okay, good enough. नहीं मैं कहीं गलत तो नहीं लिख रहा हूँ ना, that the constant wise it is right now. That is what I was
हाँ,
asking.
हाँ, sir.
Okay, good enough. So the constants I tend to forget. So mainly this is something that you okay. One of the so one of the things that I want to make clear is two things I have made clear. That first thing is that the Coulomb's expression of the force is valid only in the two conditions. The first condition that actually I talked very rapidly and actually very promptly suggested that the force between the two charges is governed by the Coulomb's law, provided the charges are in static condition. Point number one. Second, it is only true for the point charges. Okay, now there arises a problem. So for example, till now in the elementary classes, when you were taught this kind of law, teachers used to give you, let's say this is charge 5 coulomb, this is 10 coulomb, and they used to ask what is the force on 5 coulomb. So you would rapidly say, okay, the force would be K Q1, that is 5 into 10, and let's say the teacher gives you a distance, let's say 1 meter, and it's quite easy to see that the force on 5 coulomb charge can be written as K times 50 divided by distance, that is 1 plus square. And let's say everything's in SI unit. And what would be the force on writing things in magnitude? Okay, and what would be the force on 10 coulomb charge? It will be again 50 into K upon 1 square. So first thing that you need to understand is that this force is mutual. So if someone asks you what is the charge, what is the force on 10 coulomb charge, whether the force on the 10 coulomb charge will be greater than the force on the 5 coulomb charge, or the force on 5 coulomb charge is greater than 10 coulomb charge, answer is no. the force would be equal. Okay, this is first thing that you should readily realize from this particular simple example that I'm giving you right now. Okay, the first thing is that charges, the force are mutual, although if they are similar charges, then the force will act on the opposite direction. That is fine. Second, it will always act along the line joining the two charges. So basically, again, the another characteristic of this particular force is that it is a central force. It is a mutual force, it is a central force. Now, the problem arises when you have certain continuous distributions. And what do I mean when I am saying continuous distributions? Let's say I'm talking about, let's say, a rod. Okay, or let's say, and this particular rod has a completely charge filled into it in form of let's say linear charge density lambda. Let's say this particular charge is distributed over length L, and uniform distribution is there. What do you mean by uniform distribution? Uniform distribution means total charge divided by total length per low, या फिर you take infinitesimal small charge divided by infinitesimal small length. Basically, what does it mean? Let's say you have a rubber ball, and if you plug something out, let's say mass dm, from let's say volume dv, if you take this ratio and if you take the complete mass of the ball divided by complete mass of the volume, if this is same, then we say that our mass is distributed uniformly. The same thing applies when I'll be saying about charges. For example, if I say that my charge is uniformly distributed over the length, what does it imply? That total charge q divided by total length will has is same no matter how small the charge you take. Let's say if you want to take from here some charge dq and divided by the length, so dq by dl will be equals to q upon l. This ratio will remain same, and this is referred to as the linear charge density. Harshit, am I going too fast, or should I slow down?
No, sir. अभी तक समझ में आ रहा है.
So now there would be a problem. Let's say now if I ask you a very simple question, let's say this is your what do you say? This is your let's say this is your uh, rod of length L. Okay, let's say this is the rod of length L. Now don't consider this width. Okay, so I'm just right now concentrating on something like, okay, it looks as if it is a sort of cylinder. Just consider it as a rod of length L. Okay, so I'm considering a rod of length L, and where on the entire rod, even inside, like this entire rod with like infinitesimal small area, this rod of length L contains a charge q. So let's say, because this is looking as if it is a cylinder, so I'm making it quite like very very slim. Okay, now if somebody asks you what will be the force on charge q naught, now you will be perplexed. Because you know that what I suggested you was that Coulomb's law is only valid for the point charges and only valid for the point static charges. So basically, whenever you are supposed to find the force between the 2 point static charges, then Coulomb's law will come in force. But now you will be in a fix. Now you would say, how would I do it? So the answer is, try to divide this entire rod into infinitesimal small lengths. Infinitesimal small lengths or infinitesimal small charges. What you would say? You would instantly say that, okay, I'll try to divide this entire rod in infinitesimal small lengths. Why would you do that? Because you know that after all, the Coulomb's law is only valid for the point charges. What you would do, you would try to take simply a point sort of charge from here, let's say dq, and you will try to find the force due to this charge dq on q naught. So basically, you will try to find the force due to this charge dq on q naught. And after knowing this particular force, what you are trying to do, you will again take some dq from here, you will take again dq from here, and you are trying to now add all these up. So basically, in physics, in mathematics, this kind of adding, where you have this variable sort of summing, is governed by integration. It is governed by integration. Is that clear? So basically, what you're doing, you're actually variably summing, because what you know is that if I have to take this charge dq, I have to take it at some length, at some distance from somewhere. Okay, so now this, because of this charge, this dq charge, there will be some force. Because of the dq charge here, there would be some force, and adding all these up would eventually mean integrating. Okay, but eventually lead to integral. Is that clear, Harshit?
Yes, sir.
Okay. Now, this is one thing. Okay. So this is concept number one, that whenever you are trying to use the prescription of the Coulomb's charge, one has to be very cautious that it is only valid for the point charges. And in order to formulate the same thing for the continuous charge distributions, you have to understand one thing, that you will have to divide the entire thing into some small infinitesimal small charges. Now you will be asking how to do it on area. The area, you will have to take mass divided by differential area. When it comes to volume distribution, you'll have to take mass divided by volume there. Okay, so first thing that you need to define is the density. First thing that you need to define is the density. So let us define continuous charge densities at first. So now your charge can be distributed in different sense. Let's say it is divided. It is distributed linearly. So I would say that lambda is equal to dq over dl. Okay. Let's say my charge is distributed over the surface. Then dq upon ds would give you the surface charge density. Generally, it is denoted by rho, and generally it is denoted by sigma. And what is rho? dq divided by d tau, you can say, or dv you can take. So basically, it is the charge per unit volume. It is charge per unit volume. This will govern your volume charge density. This will govern dq upon ds would govern your sigma, which is the surface charge density, and dq upon dl will govern your linear charge density. Is that clear to you? I think this is quite clear. Now, let us come to a very different question. That is basically the prime interest of your JEE exam also, and your standard 12th course also. That is, what is electric field? And why do we need such a quantity? The first thing that you need to understand, what is field. Okay, field is a quantity. It is a vectorial quantity. You can say it is a vectorial quantity which will denote something in space. And when it denotes something in space means what? So this vectorial quantity will depend upon the coordinates in the space. It will depend upon the coordinates in space. Okay, and at that particular point, it will also give you the direction. It will also give you the direction. So what does it mean? So let's say okay, now again, fields are divided into two varieties. One of the varieties called as a vectorial field, and other variety is called as a scalar field. Okay, let's say you are sitting on a beach. Okay, let's say Harshit is sitting on the beach. So let's say this is your sea, and let's say here Harshit is sitting. Okay, and let's say here there is a altitude. I mean, there is a mountain with a high altitude. Okay, just near to this particular. So you know that if I tell you, okay, Harshit, go and take a sort of, I don't know what it would be called, in order to understand, in order to quantify, I think, moisture. I don't know what hygroscopic, some sort of device you have, and if you try to find the moisture here, and if you try to find moisture here, and if you try to find moisture here, moisture will actually depend upon the coordinates, that is x, y, z. Moisture will depend upon the coordinates x, y, z. Or let's say if I tell you what is the temperature, so you know that near this particular place there would be certain temperature, and as you go along high in the altitude, you know the temperature would, from your geography classes, you know that your temperature would fall down. So basically, you know that your temperature is behaving as a function of x comma y comma z. So certainly this is a field, but it does not possess a direction. So basically this is a scalar field. But what is an electric field? Electric field at any point, let's say velocity field. So let's say this is river Ganga flowing, and if river Ganga is flowing, you know that there are currents and everything is there. So you know that this particular velocity possesses a direction also. It possesses a strength also. Let's say you talk of Ganga flowing in, let's say Haridwar. So you know that Haridwar, or you let's say Rishikesh. So let's say Rishikesh. So in Rishikesh, you know that your Ganga is flowing at a very river Ganga is flowing at a very high speed, because it is just coming down from Himalayas. Now, if you try to find the velocity around at Varanasi, so you know that at Varanasi these are plains. So basically, here you will not have that amount of velocity with the with the water. So basically, the velocity vector of the fluid here would depend upon the direction. Will also have a direction sense, and will also have the sense in terms of xyz. That is, you change the coordinate, your velocity of the fluid or velocity of the water would change. So velocity here is a vectorial function, a vectorial field here. So basically, it is a vectorial field. Now, you would uh, you would think that what is happening. See, whenever you have to quantify interaction between the two charges, whenever you have to quantify interaction between the two charges, between the two charges, okay, whenever you have to quantify interaction between the two charges, you tend to ask the question, what sort of interaction? Do you want a scalar description or you want a vector description? If you want a vector description, you will say, I'll give you what is the force between the two charges. And if you say, I'll give you a scalar description, then Harshit would say, I'll give you the potential energy because of the presence of these two charges. What is the potential energy of the system? Okay. Now the same thing, when I'm saying, okay, forget about this Q2, just tell me what is about a single charge. Now, when you have to describe that due to presence of this individual charge Q1, what will be the impact in the space? What will be the impact in the space? Now you are talking of something called as field. Okay, so basically when you're talking of interaction between the two charges, you tend to describe it in two ways. You would ask very promptly the question, what sort of description you want, what sort of description you want. So for example, if somebody says, I want a vectorial description, so you would say, okay, I'll find you the force. Okay, and then somebody says, okay, no, I want a scalar description in terms of interaction between the two charges. That is, I want to know that if these two charges are present anywhere in the space, what is the potential energy of the system of them being together. Okay, so here this particular description is referred to as potential energy. And instead, if I just take one charge aloof, and then I say what is the response, or you can say what is the effect, what is the effect of this single charge here, that particular effect due to the single charge is quantified by field or potential. So instead of potential energy, you would say something called as potential, and instead of force, you would say something called as field here. In very easier language, what would I say? Let's say I have a charge Q here. Okay, what would happen as soon as charge Q is set here? It will set a field around itself. What do physicists say? They say that this, because of this charge Q, there will be some sphere of influence around this charge Q, or you would say because of charge Q, there is a field. Field means what? Again, I told you, because of this charge Q, there is some quantity which depends upon the coordinates. Now, instantly you know that if I have this charge Q here, and if I bring it in the closer vicinity to this charge Q, what would it feel? It will feel certain force depending upon the sign of the charge Q. Let's say if this is a negative charge, it will feel a force of attraction, and this is charge Q. If it is positive, then it will feel force of repulsion. But you can understand that this particular charge Q would feel different forces, and as I'll bring it very close, it will start to feel stronger force. It will feel stronger force. It will feel stronger force. But understand, force is a description when you have many charges or at least two charges. But this particular description, we don't take it into consideration when we just take the effect due to one single charge. If you want to take the effect due to one single charge, then this particular effect is governed by something called as field. And what is field? Field is, you can think it in a very abstract sense, that this is nothing but it is the sphere of influence. Sphere of influence. I'll write it here. This is sphere of influence here. Just in very abstract sense, I'm saying. Okay, not exactly the same, but I'm just trying to say that as you set up a charge Q, there sets up a field around it. There is a sphere of influence, which will actually interact with other charges. So basically, the charges don't interact, rather their fields would interact. Okay, so it's not a charge one-to-one interaction nahi ho raha hai. It is basically the field and field are interacting. Okay, and another thing that you need to understand is this. Now, this is in a very abstract sense that you are saying. In a very abstract sense, you are saying. So the question arises: how to probe this field? How to probe this field? Or how to prove this field strength. This is very much clear that if you bring this charge Q very close to this charge Q, it is going to feel very much force of repulsion, provided they are of same sign. Okay, so how to prove this field strength? So what has been devised is, let's say this is your source charge. Okay, let's say this is your source charge, and we want to find what is the field due to this source charge Q. What is the field strength due to this source charge Q? So what would one do? How to probe it? So the prescription is very simple, that we'll try to bring a test charge. We'll try to bring a test charge. Now you would say, if I bring a very big charge, then it will distort the field, isn't it? It will distort the field. Distort, samajhte ho na? It will distort the field. So what is the prescription? The prescription is bring this particular test charge as small as possible. Bring this test charge as small as possible. So bring this test charge as small as possible and try to find the force this charge Q exerts. So what is the force that charge Q exerts on this Q naught? This will be K Q naught upon R square. Now, what is the field due to this charge Q? The field strength is defined as, let's say these two charges are of same sign, and let's say this is a positive direction of R. Let's say this is R cap. So what will be the field due to charge Q? It is nothing but it is equal to the limit Q naught tends to 0, K Q naught divided by Q naught R square. So what it is actually nothing but it is equals to the force vector divided by the magnitude of the test charge. So basically what is the field strength? Field strength is given by limiting value Q naught tends to 0. What is limiting value Q naught tends to 0? Why I'm saying it? Because we need that whatever test charge we are bringing, we should bring it as small as possible. We should bring it as small as possible. Is that clear?
Yes, sir.
Okay, and usually you would find teachers writing in this not writing in this very intricate form. So they would say the field due to a point charge Q is given by KQ upon R square. So this is the field due to a point charge Q anywhere in the space at a distance smaller. Is that clear? So at times you would find this, and another expression probably in NCRTs or otherwise you will find what is field. One would say field strength is nothing, is the force, field strength, electric field strength of charge Q is the force exerted by charge Q on a unit coulomb charge. Okay, this is what has probably would have you would have known. Now you'd see that what sort of definition I have given and why this is written. This is also same. This is equivalent to writing what I've written there. See, if I want to find force from the field, what I am supposed to do? So basically, what am I supposed to do? So here, what is the force on Q naught? Force on Q naught is nothing, but it is equal to force on Q naught is nothing, but it is equal to Q naught times electric field, isn't it? Force on Q
Yes,
naught
sir.
is nothing, but it is equal to what? Q naught times electric field. You just multiply Q naught, you will get force on Q naught, isn't it?
हाँ सर.
अब अभी तुमने क्या पढ़ा? इलेक्ट्रिक फील्ड का एक्सप्रेशन क्या है? इलेक्ट्रिक फील्ड ऑफ चार्ज Q इज नथिंग बट इट इज इक्वल टू K Q अपॉन R स्क्वायर R क्या. और तुम थोड़ा ध्यान से देखो Q नॉट से तो Q नॉट कैंसिल हो जाएगा, तो इफेक्टिवली क्या है? इट इज इक्वल टू मल्टीप्लाइंग 1 ओनली ना. सो जस्ट मल्टीप्लाई इट बाय 1 कूलम चार्ज. If you multiply it by 1 coulomb charge, this will become what? This will become force exerted on the unit coulomb charge. Okay, or force exerted on a unit charge. This will give you the force exerted on the unit charge. So whenever you feel like finding field, what is the prescription? You will ask anybody. Let's say if somebody says, what is the field due to this particular ring at distance, let's say r from the axis. So you would say, just I'll place a charge of 1 coulomb here, and I will try to find what is the force exerted on this particular unit charge. And once I know what is the force exerted on this particular unit charge, I will be able to find the electric field due to this particular ring. Is that clear? Similarly, if someone asks you, if I give you a sphere, and if I ask you what is the force exerted at what is the field at point r, from the center of this particular sphere. So you will say, I will just place a 1 coulomb charge here, and I will try to find what is the force on this 1 coulomb charge, which is at a distance r away from the center of this particular sphere, and I will be in a position to find the electric field. Is that clear?
Yes, sir.
Okay, so now I'm going to start with some very difficult some questions where I'm going to do electric field of continuous system. Is that clear, Rashid? So we'll start it in the
Yes.
next session. Okay.
Yes.